Now, progress in microprocessors did not stop in 1985, of course, just because the transistors are now too small to see with even the most powerful visible light microscope. That's not going to stop people. In fact, Moore's law had become a sort of self-fulfilling prophecy. It had been going on for so long by this point that people assumed it would keep going, and they built their plans according to it. They might say, okay, well, what do we need to develop in the next 2 years that will make the microprocessors half as big, and what do we need another 2 years from now, and another 2 years from now, and they'd start the research programs with the aim of achieving this. And there were many different forms of research that went on. Almost every area of physics and chemistry is involved. One thing is that you can't use photolithography, light, to make patterns that are much smaller than the wavelength of light. So they couldn't use visible light anymore. They had to use shorter and shorter wavelengths. They went into ultraviolet and then mid-ultraviolet and then far ultraviolet. They no longer generally put the dopants in the boron or whatever just by heating the whole thing up and letting it diffuse, and that's too uncontrolled. Now they'll use ion beams to implant them. So they fire the ion beam to put the doping chemicals in at just the right depth. Then they have to heat the whole thing up to repair the damage to the crystal that was caused by these ion beams hitting it. They're building more and more layers, and sometimes they use old-fashioned polishing or washing to get, say, rid of a layer of photoresist, but nowadays they'll often use plasmas to etch away different layers. So they might put the photoresist and then use a plasma to cut away underneath so they can now lay down a new layer of wires, whatever it might be. They needed new chemicals for insulation layers. As these components got smaller and smaller, more and more electricity started leaking through the insulation or having capacitance across it. So you needed low dielectric constant or high dielectric constant insulators and other components. So that the chemicals used became more and more exotic and complicated and often very toxic. By 2010, components were down to about 100 nanometers, 0.1 micrometers. It's another 100 times smaller than even the things that were too small to see with the microscope, which means you could get billions on a chips. But where do you go now? But even by this point, a fab, a plant to produce them, is costing billions of dollars. One issue now was this whole field effect transistor. Remember, you have the different p-type and n-type and the inversion layer and the electrons moving through it. But at this point, you're starting to get quantum tunneling and you're starting to get too many electrons going the wrong way. It's just so small. These are only hundreds of thousands of atoms across. So what they came up with is the FinFET. So FET is field effect transistor. A FinFET is where the field effect transistor is vertical and the electrode is now, the gate is now wrapped around it on 3 sides, and this prevents so much of the leakage of current. This is what's necessary to get below these scales of hundreds of nanometers. But it's much more complicated to build. You need many more steps of laying things down, etching away, laying things down, etching away, laying things down, etching away to build this 3-dimensional structure. But this is what most cutting-edge chips nowadays use. Another problem was that they were using ultraviolet light with the wavelength of about 190 nanometers, but that's just too big to make these small things. So a number of organizations decided to bet on making the components smaller by going to extreme ultraviolet. This is ultraviolet with a wavelength of only 13.5 nanometers. Most people would call these X-rays. How could you produce light with this incredibly short wavelength and use that to make the masks? If you can do it, it can make the masks much smaller and help you shrink the size of the components. The trouble is these wavelengths cannot penetrate air and they cannot penetrate lenses. So you have to do all your photolithography now in a hard vacuum, pump all the air out. You need this incredibly extreme ultraviolet. No one was quite sure how to produce it. Several different approaches were taken from synchrotrons. What they currently use is they fire tiny droplets of tin, 50,000 tin droplets per second, and in precise synchronization, these tin droplets are hit by very powerful lasers that vaporize them, making them briefly hotter than the surface of the sun, much hotter than the surface of the sun, producing a steady stream of flashes, which produces the extreme ultraviolet. But this required the most powerful carbon dioxide lasers ever made, and as most of the energy that goes into it doesn't go into the laser light, it goes into heating the whole thing up. They needed a new cooling system that could keep these lasers from melting. Normal fans couldn't go fast enough, so they invented a new type of fan that was magnetically suspended, because otherwise the bearings would wear out. So magnetically suspended fans to cool down this incredibly powerful laser that fires 50,000 times a second, actually more than that. There are multiple pulses used for each vaporization, and all these tin droplets just to produce the ultraviolet. Once you've got the stream ultraviolet, you need to focus it on the mask. The trouble is you can't use a lens. They have to use mirrors, but even most mirrors, these X-rays, extreme ultraviolet will go through them. The mirrors had to be the most precise pieces of equipment ever built, with multiple layers deposited on, so the interference between these nanometer soft X-rays, extreme ultraviolet, so they can focus the entire thing. An incredible technological challenge. And you need the same sort of technology on the masks. So each mask is now $100,000, and you might need 800 masks to make one chip. So the current chips, tens of billions of transistors on each chip. Each is tens of nanometers in size, so only hundreds of atoms across. A modern fab to build these things costs about $20 billion. Only 2 or 3 companies in the world make the current cutting edge ones. One, TSMC, completely dominates, though Intel and Samsung can also make them to some extent. There's also a great problem with reliability. You lay down multiple layers. You have the layers of the transistors, which might take 10 or so masks to make, to build up layer by layer all these FinFETs. And then you have to build wires and connectors to join them up on further layers. So overall it might have 50 layers or 100 layers, each of which takes maybe 10 steps to make. You have to polish everything, clean it, deposit the photoresist, which will be done in one machine, then apply the light, done in another machine, wash away, another machine, deposit whatever's new, maybe build new crystals or lay down a metal layer only in the right place, then polish it all flat, and then do it all over again. So there typically can be many hundreds to even 1,000 different steps. And if you're doing 1,000 steps to build one of these things, each step has to be unbelievably reliable. It's not enough to be 99% accurate in each step, because 0.99 to the power of 100 is 0. If you're 99% reliable, you've got 800 steps, you will never have a working chip. The yield will be incredibly low. So there's a huge amount of work at making every step not merely 99, but 99.9999% reliable, because you need that to combine the multiple hundreds of steps to build a working chip. It's so difficult. Where are we going in the future? Well, of course, people started many years ago in developing things to help keep Moore's law going for the next generation. There's high aperture extreme ultraviolet, so making the extreme ultraviolet machines focus better and give more precise detail. Instead of having the gate around 3 sides of a transistor, you actually use around all 4 sides as you make the transistors smaller. You can now maybe stack chips in 3 dimensions on top of each other, and you have better chip designs where, for example, the memory and the logic are on the same chip close to each other. Going further into the future, it might be we're going to use new semiconductors, stop using silicon and use something else. There may be optical chips where signals are passed from one place to another by having lasers built into the chip that send light down optic fiber cables built into the whole thing. Or, of course, there could be quantum computers. That's quite a ways off, but in principle, a quantum computer, even with only a very few bits, can solve things that no normal computer can, like cracking cryptography. So lots of people are thinking about where the future would go. It's not clear to stop, but it is clear that going further is going to be very expensive.